In the present video, we will discuss the traveling salesman problem. The traveling salesman problem is one of the most common optimization problems in operations research. Suppose a salesman has to visit n number of cities, then he starts from one city, visits each city only once, and finally returns to the starting city. For example, he started a city, let's consider A, then he should be returned to the city A. So the main objective is to find the best route so that the total traveling distance, time or cost is minimum. Number of possibility of routes are if there are the two cities, only one possible route. So if two cities, let's consider A and B, then possibility of the route is A to B. Suppose there are the three cities and possibility of routes are the two. Let's consider A, B, C are the cities has to be travel. Then possibility of the route is A to B, B to C or A to C, C to B. So in general, for n number of cities, there are the n minus 1 factorials possibility of the routes. So goal of the traveling salesman problem is find the route with the minimum total traveling cost or the minimum total distance. Let's consider there are the four cities A, B, C, D and distances are given. Then possibility of the routes are 4 minus 1 factorial, that is the 3 factorials. So 6 possibility of the routes are there, that is the ABDCA, ABCDA, ACBDA, ACDBA, ADCBA and ADBCA. So these routes are the possibility of the routes. Then distances are the 108, 97, 141. Similarly 108, 141 and 97. So among the all the routes, we have to select the minimum distance. So we have to select the optimal route is ABCDA or ADBCA. So this is the traveling salesman problem. Let's consider Cij is the cost, distance or time required to travel from city I to city J. And Xij is the decision variables. And decision variables equal to 1 if the salesman travels from city I to city J. And salesman travels from city I to city I or city J to city J, then it is equal to the 0. So Xij is the decision variables. It is the one when salesman travel from city I to city J, otherwise you have to consider the 0. Then objective function of the traveling salesman problem is the objective is to minimize the total traveling cost or minimize the total traveling distance or time. Let's consider Z is the objective function, then Z equal to the summation of I equal to 1 to n and summation of j equal to 1 to n Cij Xij, where Z equal to the total traveling cost or distance or time. Then objective is minimize Z. Let's see the constraints of the traveling salesman problem. First constraint is the leave each city only once. So leaving, so that's why I have to consider j equal to. So summation of j equal to 1 to n, xij equal to 1, where I equal to 1, 2, 3 up to the small n. Similarly, second constraint is enter each city only once. So entering, then we have to consider summation of I equal to 1 to n, xij equal to 1, where j equal to 1, 2, 3 up to the small n. Third constraint, visit every city only once. The route should be selected in such a way that no city is visited twice before all cities have been visited. This condition eliminates subtours and ensure that the salesman completes one complete tour covering all cities. So let's see the last constraint. No travel from a city to itself. So the salesman cannot travel from a city back to the same city. Therefore, CII equal to the infinity. This means the diagonal elements of the cost matrix are assigned a very large value so that they are never selected. So these are the constraints of the traveling salesman problem. Let's see some important notes on traveling salesman problem. The traveling salesman problem is very similar to the assignment problem. In assignment problem, each person is assigned to one job. Similarly, in the traveling salesman problem, there is one extra condition, that is, salesman must complete one continuous tour by visiting every city exactly once and then returning to the same city. Therefore, traveling salesman problem can be considered as an assignment problem with an additional constraint, that is no subtour constraint. So let's see the objective and rules of the traveling salesman problem. So objective of the traveling salesman problem is minimize the total traveling cost, distance or time. Rules are the start from any one city, visit every city exactly once and return to the same city. Do not visit the same city twice. Do not travel from a city to itself. Complete one continuous tour without forming sub-tours. So these are the rules of the traveling salesman problem. Let's see the one example problem. A traveling salesman has to visit 5 cities. He wishes to start from a particular city, visit each city once, and then return to his starting point. Cost of going from one city to another is shown below. Find the least cost route. So let's see the solution. So this traveling salesman problem we can be solved by applying the Hungarian method. So apply the Hungarian method in two phases. First phase is there are the two steps. First step is subtract the minimum value of each row from the entries of that row. So first we have to determine the minimum value from the each row. In the first row, minimum value is the 2, and in the second row, minimum value is the 4. Third row, minimum value is the 8. Fourth row, minimum value is 8. And fifth row, minimum value is the 2. So note down all the minimum values: 2, 4, 8, 8, 2. Then subtract these values from the respected row. Then so write down the new tabular column and subtract the 2 from the first row elements. Then first row elements will become the, so infinity minus 2, so it will become the infinity only. Then 4 minus 2, 2, and 10 minus 2, 8, 14 minus 2, 12, 2 minus 2 equal to 0. Similarly, in the second row, we have to subtract the value 4. Then second row elements will become the 12 minus 4, which is equal to the 8, and infinity minus 4, which is equal to infinity only, and 6 minus 4 equal to 2, 10 minus 4, 6, 4 minus 4, 0. Similarly, third row elements, so have to subtract the 8 from the third row elements. Then third row elements will become the 16 minus 8, which is equal to 8, 14 minus 8, 6, infinity minus 8, which is equal to infinity, and 8 minus 8, 0, and 14 minus 8 equal to the 6. And similarly have to subtract the 8 from the fourth row elements. Then fourth row will become the 24 minus 8, which is equal to the 16, 8 minus 8, 0, 12 minus 8, 4, infinity minus 8, infinity, 10 minus 8 equal to 2. And fifth row elements, we have to subtract the value 2. Then fifth row will become the 2 minus 2, 0, 6 minus 2, 4, 4 minus 2, 2, 16 minus 2, 14, infinity minus 2, which is equal to infinity. So this is the tabular column after completion of the step 1 in the phase 1. Next we will go for the step 2. Subtract the minimum value of each column from the entries of that column. So have to subtract the minimum value from the each column. So first I have to determine the minimum value. So minimum value in the first column is 0, and in the second column 0, third column is the 2, fourth column and fifth column minimum values are the zeros. So once again I have to write down the new tabular column. So in the first column I have to subtract the 0. So it will become the same values. So that is the first column, infinity, 8, 8, 16, 0. Similarly, second column elements also there is no change. So that is the 2, infinity, 6, 0, 4. And in the third column elements we have to subtract the 2. Then 8 minus 2, 6, 2 minus 2, 0, infinity minus 2, infinity, 4 minus 2, 2, 2 minus 2, 0. And in the fourth column, fifth column, it will be not changes the cell values because minimum value is the 0. So this is the final table after completion of the phase 1. Next we will go to the phase 2, that is the optimization of the problem. First step is draw a minimum number of lines to cover all the zeros of the matrix. First I have to go for the row scanning. So in the row scanning, mark a square around the 0 and draw a vertical line passing through that 0. If row is having the more than one 0, have to skip the respected row. So I have to go for the row scanning. First I have to go for the first row. So in the first row there is only one 0. Then mark a square and draw a vertical line. Then in the second row also there is exactly only one 0. Then mark a square and draw a vertical line. Similarly in the third row also there is only one 0. Mark a square and draw a vertical line. And fourth row also there is only one 0. So mark a square and draw the vertical line. And fifth row also there is only one 0. Mark a square and draw a vertical line. So after scanning of the last row, check whether all the zeros are covered with the lines. If yes, go to step 2. Otherwise, do column scanning. Here, after scanning of the fifth row, all the zeros are covered with the lines. Then, no need of the column scanning. Directly have to go for the step 2. So, step 2 is check whether the number of square marked is equal to the number of rows of the matrix. Here, number of square marked are the 1, 2, 3, 4, 5. And number of rows are 5. So, square marked zeros are equal to the number of rows. Then we got the optimal solution. Then step 3 is treat the solution as marked by the square. So optimal assignment will become the A to E, and next to E to A, then B to C, C to D, and D to B. So we know the rules of the traveling salesman problem. Always starts from any one city. then visit every city exactly once and return to the starting city. Do not visit the same city twice. Do not travel from a city to itself and complete one continuous tour without forming subtours. So here observe that traveling salesman first started from city A, then he reached to city E, then once again he reached to E to A. So A, E, A. So he started from city A and reached to the city A, but he is not covered the remaining cities B, C, D. So the salesman should go from A to E and then come back to A without covering the cities B, C, D. In this regard, this solution is not the solution to the traveling salesman problem, as it gives the sequence AEA. So this violates the condition that salesman can visit each city only once. By applying the Hungarian method to this problem is not a best solution. The next best solution to the problem can be obtained by bringing the next non-zero minimum element. So we have to bring the minimum non-zero element as the assignment. Here minimum values after the 0 are the 2 are the cells of A to B and D to C and D to E. Then we have to make a unit assignment in the cell AB instead of 0 assignment in the cell AE. So which means we have to make a new assignment for the value 2 at the A to B cell as the assignment instead of 0 at the A to E cell. So we have to select the 2 as the assignment instead of the 0. So that 2 value is in the AB cell instead of the 0 value in the cell of AE. Okay, so next we have to go for the regular scanning. So first I have to go for the row scanning. So for the first row, so 2 is the our assignment. So we have to mark a square for the 2. Then we have to draw the vertical line. Next we have to go for the second row. There are the 2 zeros. So I have to skip the second row. And third row there is only 1 zero. Mark a square and draw a vertical line. And in the fourth row there are the no zeros. So I have to skip. And fifth row also there are the more than 1 zero. So we have to skip the fifth row also. So next I have to go for the column scanning. For the first column, so there are the only 1 zero. So then I have to mark a square and draw a horizontal line. And the second column already we are removed in the row scanning. And in the third column there are the only 1 zero. So mark a square and draw a horizontal line. And fourth column already we are removed in row scanning. And in the fifth column, so 0 is there, but we are not considering this is the assignment. Instead of this one, we have to select the 2 is the assignment. So I have to select this 2 as the assignment and mark a square and draw a horizontal line. So now here, so number of rows are the 5 and number of square marked are equal to the 5. Then we got the optimal solution. So then optimal assignment is the A to B, then B to C, then C to D, then D to E and E to A. So optimal assignment is the A to B, B to C, C to D, D to E and E to A. So sequence is the A, B, C, D, E, A. So here traveling salesman started at a city A and finally he reached to the same city, and he did not travel the twice any city. So this is the optimal assignment. Next, to calculate the optimal cost. So for this one, observe the given tabular column. So A to B cost is the 4, and B to C cost is the 6, and C to D cost is the 8, and D to E cost is the 10, and E to A cost is the 2. So total optimal cost is the 4 plus 6 plus 8 plus 10 plus 2, which is equal to the 10, 20, 30. So this is the solution, and thank you.